Welcome to this lecture. Over the last few lectures, we have been looking at the real time schedulers. Initially started with the simple task schedulers, which are the clock driven schedulers, then looked at the event driven schedulers, and we identified two important schedulers, the rate monotonic scheduler and the earliest deadline first scheduler. And between these two, we said that rate monotonic scheduler is overwhelmingly popular, being used in many applications and also directly supported by the real time operating systems. To start with, we simplified the problem. We considered the task set is independent, and then slowly we were trying to make it applicable to realistic applications. And in the last class, we were looking at the problems that arise when tasks share resources, non-preemptible resources, and we had identified that the traditional operating system of semaphore does not work well. The problems that are faced are priority inversion and unbounded priority inversion. Priority inversion as it is can be solved by careful programming, by reducing the time for which a low priority task uses its critical section. But unbounded priority inversion is a very severe problem, and many applications in the past have failed for not properly addressing the unbounded priority inversion problem. We had explained what exactly is the problem, and then we were looking at the solutions. The simplest solution is the priority inheritance protocol, where a low priority task inherits the priority of high priority task waiting for the resource. We saw in the last lecture that this protocol, the simple priority inheritance protocol, does overcome the unbounded priority inversion problem, but then it introduces some problem and also does not address well some other problems. Now, let us first identify these disadvantages of the basic priority inheritance protocol, then we will look at more sophisticated protocols. So, let us look at the shortcomings of the basic priority inheritance scheme. There are two important drawbacks of the priority inheritance protocol. The first one is chain blocking. We will see what exactly is chain blocking, and then the second is it does nothing to prevent deadlocks. So, when we use the basic priority inheritance scheme, the tasks may get deadlocked, but we will see that more sophisticated algorithms, which are basically improvements over the basic priority inheritance protocol, they overcome these problems. First, let us try to see how deadlocks occur when the priority inheritance protocol is used. Let us assume that there are two real time tasks T1 and T2, and both of these tasks need two resources. T1 needs both CR1 and CR2, and T2 also needs both CR1 and CR2. And let us assume that by the rate monotonic scheme, T1 has higher priority than T2, but then T2 starts running fast because there are no jobs for T1. because T1's phasing is later than T2, or maybe that T1's instant has just completed and T2 is starting to use. Now, T2 runs first, and then these are the sequence of operations they undertake. T2, it executes the instruction lock R2, and since the critical resource R2 is available, it can successfully lock R2, and then it does some extra processing, some other processing it does. By that time, the task T1 instance arrives. Being a higher priority, it preempts T2, but then after some local processing it locks R1 and then does more processing using R1 and then needs the resource R2, and when it locks R2, R2 has already been locked by T1, and therefore, R2 has already been locked by T2, and therefore, T1 blocks, and then T2 gets the control. T2 starts executing, it does some executions using R2, but then it needs R1, and as it tries to lock R1, R1 is already locked by T1, and that is the deadlock situation. So, using the basic priority inheritance scheme, deadlocks can arise. Of course, you can see here that once T1 blocks on T2, T2's priority increases to T1, but that does not help, still the deadlock arises. Now, let us look at the second problem that the basic priority inheritance scheme suffers from, goes by the name chain blocking. First, let us see what do we mean by chain blocking. The chain blocking arises when a task needs a number of resources, and the chain blocking causes each time the task needs a resource, different resource, it undergoes priority inversion. That is, if a task needs n resources, each time it requests for one of the resources, it undergoes inversion, waits for that resource, and by that time lower priority tasks execute and multiple priority inversions occur. And in the chain blocking situation, when a task needs multiple resources, the waiting time altogether can be very high, and a high priority task can easily miss the deadline. So, chain blocking is a severe problem. Now, let us throw a schematic diagram. Let us try to understand what exactly is the chain blocking. Let us assume that the highest priority task T1 needs several resources. Let us say it needs 2 resources. So, task T1 initially blocks for CR1 because T2 is holding CR1 and CR2. After some time, T2 releases CR1 and T1 starts executing, but then after some time it needs CR2 and again it blocks for CR2, but in the process it undergoes priority inversion. So, a high priority task under the priority inheritance scheme can undergo multiple priority inversion if it uses multiple non-preemptible resources. But we will see that more sophisticated algorithms overcome the chain blocking problem. this is another more generalized example. Let us assume that task T 1 is a high priority task. It does some local processing without using resource, then it needs the resource R 2, and then it does further processing using R 2, then it needs R 3, then it needs R 4, and so on. Now, let us assume that there are several lower priority tasks which need these resources. For example, T 2 needs the resource R 2, it does some processing with R 2, T 3 does processing with R 3, T 4 with R 4, T n minus 1 with R n minus 1, and T n needs the resource R n. Now, let us assume that initially the task T n, which is the lowest priority, starts executing and it locks R n. Similarly, all other tasks, they lock their resources, and at that instant the task T 1 arises, an instance of T 1 arises. It does some processing initially, but then it needs the resource R n, gets blocked. It needs the resource R 2, and R 2 is already locked by T 2, and therefore, T 1 gets blocked. Now, T 2 starts executing because T 1 has blocked and CPU becomes available, and it does local processing and releases R 2, and then T 1 gets R 2, starts processing and needs R 3, which is held by T 3, and so on. So, for all the n resources, it undergoes priority inversion one after the other. What is the maximum time that it gets blocked? The maximum time the task T 1 gets blocked is equal to the time for which each of these holds, is the sum of the time for the duration for which each of the tasks holds their respective resource. For example, for this situation, the total blocking time for the task T 1 due to the n resources will be the time for which T 2 uses the resource R 2, T 3 uses the resource R 3, and so on, and T n needs the resource R n, which can be large. So, chain blocking is a severe problem in the simple priority inheritance scheme. The simple priority inheritance scheme, as you will see, requires very minimal support from the operating system, and therefore, in simple applications it is actually used. But then the programmer, the designer of the application must keep in mind these two severe problems that they might face, the deadlock problem and the chain blocking problem. Now, let us look at some properties of the simple priority inheritance protocol. Let us say a task T A needs a resource which is used by k other lower priority tasks. Let me repeat that a task T A needs a resource, a non preemptible resource, which is also used by k lower priority tasks. Then under the priority inheritance scheme, what is the maximum duration for which the task T A may suffer priority inversion? The answer is that it is maximum of the execution time of the k lower priority tasks for which they need the resource, the non preemptible resource. If E I is the time for which the task T I needs the resource, then the worst case blocking time for the task T A is maximum of E I, considering all the tasks T I. The second theorem is that if a task needs k resources, the first one we had looked at one resource needed by a task, here a task needs k resources, and each of these k resources is used by several of the lower priority tasks. Now, what will be the total waiting time for the task T A in the worst case? As you can see that this is a generalization of the first theorem, and also we know that the priority inheritance scheme suffers from chain blocking. So, for each of the resources it requests, it may undergo blocking. So, it will be sum of the maximum of E I for each of the resources. If there are 3 resources and these 3 resources are used by different sets of lower priority tasks, then the total blocking time for the high priority task in the worst case will be the blocking time for the first resource plus the blocking time of the second resource plus the blocking time of the third resource, where the blocking time for each resource is given by theorem 1. Now, let us look at some improvements to the basic priority inheritance scheme. We have seen that the priority inheritance scheme is a simple but powerful protocol. It does overcome the unbounded priority inversion problem, which is a severe problem, can cause tasks to miss their deadline, but then we saw that it is rather too simple and suffers from 2 major problems, the deadlock problem and the chain blocking problem. Now, let us look at the first improvement, which is done by the highest locker protocol. In the highest locker protocol, there is also a priority inheritance scheme, but it is slightly different. Here, for each resource that is under use by a task, a ceiling priority value is assigned. The ceiling value is computed as the highest priority task that can use that resource. So, let me repeat that the main idea in the highest locker protocol is that a priority value is assigned to a resource. It is called as the ceiling value for that resource, which equals to the highest priority task that may ever use that resource. Now, let us look at an example. If R is a resource and is used by 3 tasks T 2, T 5 and T 10, and let us assume that T 10 let us assume that T 2 is the highest priority task. Then for the resource R, there is a ceiling value assigned which is equal to 2. And the highest protocol requires that when a task requests a resource, then the priority of that the task is raised to the ceiling value. For example, if the resource R is available and let us say the task T 10 gets the resource R, requests and gets the resource R, then T 10's priority value will be raised to 2. In the highest locker protocol, each resource is associated with a ceiling value, and as soon as any task locks the resource, the priority of that task becomes equal to the ceiling value. We can easily see that this protocol overcomes the shortcomings of the basic priority inheritance scheme, but then it introduces a very difficult complication. We will see what is the complication a little while from now, but then we will also look at an improvement to the highest locker protocol, which is called the priority ceiling protocol, that overcomes the not overcomes to large extent overcomes the problem that highest locker protocol introduces. The highest locker protocol is a small improvement of the basic priority inheritance scheme, and if we understand the highest locker protocol, then it becomes easy to understand the ceiling protocol, the priority ceiling protocol. The priority ceiling protocol by itself is little more complicated than both the priority inheritance scheme and the highest locker protocol, and if we know the two protocols, the priority inheritance protocol and the highest locker protocol, then it will become very easy to understand the working of the priority ceiling protocol. But then the priority ceiling protocol is the best protocol, even though it is slightly more complicated, but it largely overcomes all the problems of the basic priority inheritance scheme and the highest locker protocol. In the highest locker protocol, during the design of an application, what are the tasks and what resources they need is analyzed, and then a ceiling value is assigned to all critical resources. And whenever a task acquires a resource, a critical resource, its priority becomes equal to the ceiling. And that is the simple protocol. Let me repeat again that during the design of the system, all the critical resources are assigned a ceiling value. The ceiling value is equal to the highest priority task that may ever use that resource, and each time a task, a lower priority task or any other task acquires the resource, its priority increases to the ceiling value. That is the inheritance scheme here, that as soon as a task acquires the resource, its priority value increases and becomes equal to the ceiling value associated with the resource. Let us look at an example. Let us assume that there is a critical resource R, and the resource R is being used by 3 tasks, T1, T2 and T3, and there will be a ceiling value associated with the R, which is equal to the maximum of the priorities of T1, T2 and T3. Let us see schematically how does the protocol work. We have these, let us assume that T1's priority is 5, T2's priority is 2 and T3's priority is 8. Now, what will be the ceiling value that will be associated with R? Let us assume that 2 is the highest priority and 8 is the lowest priority. In that case, the ceiling value associated with the resource R is equal to 2, because 2 is the highest of 2, 5 and 8. So, the ceiling value that will be associated with R is 2. But one thing I need to clarify is that sometimes we are saying that 2 is the highest priority, and at some other time we are using 8 as the highest priority. Actually, the confusion arises because different operating systems, they use different conventions. For example, in Microsoft Windows and some other operating systems, the priority value is the higher the priority, the higher is the priority value. So, T10 will have higher priority than T5 or T1. So, the higher the priority value, the higher is the priority. T10 is higher priority than T5 or T1, whereas in Unix and the Unix derivative operating systems, the exactly reverse is the convention. A lower priority indicates higher priority, a lower priority value indicates higher priority, and a higher priority value indicates lower priority. So, if a task is used by a resource is used by 3 tasks T2, T5 and T8, then the ceiling value will become 2, because 2 is the highest priority, whereas in operating systems such as Windows based operating systems, it will become 8, and that is why we have been using these two different conventions. The protocol is simple. Once the ceiling values are associated with resources, each time a task acquires a resource, it inherits the ceiling priority, and then as it relinquishes the resource, it completes processing with the resource and releases the resource, then it gets back its earlier priority. This protocol helps to overcome the problems of unbounded priority inversion, deadlock and chain blocking, but then it creates a new problem which is called as the inheritance blocking. Let us look at an example. Let us assume that the resource R is a critical resource used by 3 tasks T1, T2 and T3, T1 with priority 5, T2 with 2 and T3 with 8, and the ceiling value associated with the resource is equal to 2. And the resource was available and acquired by T1 whose priority is 5, and T2 blocks on the task T1, T1's priority becomes 2, and then the tasks T4, T5 etc., these are higher priority than T1, but then since T1's priority is increased, they cannot really get the CPU, because T1's priority has been increased, and T4, T5 etc. undergo inversion, and that we call as inheritance related inversion. T1 as soon as it acquires the resource, its priority increases to 2, and the other tasks needing the which are ready, but higher priority than T1 cannot get CPU and they undergo inversion. We call it as the inheritance related inversion. Now, we are at the end of the lecture, we will stop at this point and we will continue in the next lecture. Thank you.